How can a system increase in complexity without guidance from an outside source? Creationists claim that complexity requires a designer, but we know that this is not true from biology, and it's also not true for geology. Patterns can emerge from processes that are random, completely stochastic, and we see this all around us. There's a word for this that scientists use, and it's emergence. Emergence is the process by which complexity can come out of processes that are random in nature. But this doesn't mean that the entire process as a whole is random. That is, if you were to just say natural selection is random, this is really missing the point because those random mutations are selected for. So on the whole, the process creates something which is not random at all, our cells. And the stochastic processes that govern landform development are very similar, fundamentally stochastic, but when certain things are selected for, not in the same way as in biology, but you'll see what I mean, these processes grow and become more complex with time. I was blown away when I saw this picture. These are sorted stone stripes which occur completely naturally in alpine and polar regions that have either a certain kind of frost called needle ice or permafrost. Here's what the needle ice looks like. It's long and fibrous, and it forms underneath the rocks and can actually push them up off the ground, and then they can topple, so that's how the rocks move. And the needle ice preferentially forms in regions where there's soil versus regions where there's stones. So in regions where there started out to be fewer stones, needle ice will tend to form in those regions and move the stones out of there. And then when the stones end up in regions where there's already lots of stones, they don't move. So why do you get the stripes? Well, when you put this all on a hillside, you tend to get stripes oriented alongside the hillside gradient, that is, they're running up and down the slope. This has to do with the fact that the rocks preferentially topple in the direction of the slope. If you don't put this on a hill, you don't get stripes at all. In fact, you get all sorts of other neat patterns. You can get sorted circles, you can get polygons, sometimes you even get labyrinth-like features. These patterns take decades or even centuries to form over multiple frost cycles, and we understand how they form and can reproduce these patterns in computer simulations that are fundamentally stochastic in nature. In these simulations, we see that small variations in initial parameters are basically amplified by the frost cycle. There are lots of other examples in geology where small initial variations are amplified over time, and patterns or complexity naturally emerges, or another way to say is self-organizes. Another example is ice wedge networks, which is the pattern expressed on the ground of the ice breaking below the surface. Sand dunes are a particularly nice example of the feedback between topography and wind. So here you can have crescent dunes or star-shaped dunes depending on the wind patterns. And again, there's beach cusps, which show how the pattern can emerge even when the beach was originally flat, and they've actually done this experiment where they flatten the beach and they can watch the pattern slowly start to emerge. One of my favorite examples is river meandering. If you've ever looked out of the window of a plane and seen rivers that look like this, probably wondered as I have, why doesn't the river just flow straight? Wouldn't that be a much more efficient way to transport the water downhill? But the reason rivers meander is because the water flows faster around the outside of a bend than on the inside. So whenever there's a curve, it tends to erode the outside of the curve faster, thus making it more curvy over time. But eventually it gets so curvy that it actually intersects itself, and this cuts off the process. So here you can see in this picture there's an oxbow lake is being formed, which was just cut off as the river got too curvy. And there are some really cool simulations that have been done that can reproduce the shape that real rivers have. And the cool thing about these simulations is that they show over time the sinuosity of the river. That's a mathy word for how curvy it is. It's defined as the path length of the river divided by the length of the valley, or the length of the river divided by how long it would be if it was straight, basically. The sinuosity of the river approaches pi as time increases, as time goes to infinity. I guess that's not too weird. I mean, pi shows up in all sorts of crazy places, but pi is the sinuosity of a circle, so it's not a crazy place for pi to appear, but I still think it's really cool. So we see in geology, just as in biology, that very small incremental changes over time can give rise to extraordinary structure.